Now there's a very useful little equation that we can use to look at the rate of blood flow. And it's based on an equation which is called Darcy's law of flow. And that's quite simple. Flow is equal to delta P over R. Delta P, that's a change in pressure. That's our pressure gradient. And R represents resistance. In fact, you can use Darcy's law of flow for the flow of any fluid in a tube or in a system of tubes, as long as that flow is laminar, which is normally the case within the body. So you can apply this very simple equation not just to the flow of blood in the blood vessels, you can also apply it to the flow of air within the bronchi and bronchioles, for example, when we talk about respiratory physiology, because air counts as a fluid as well. A fluid is a liquid or a gas. So this is a very important equation, but if we're talking about the cardiovascular system, we can refer to its terms in slightly different ways. The flow, well, that's the rate at which blood is moving around the cardiovascular system, and we can refer to that as cardiac output. Cardiac output is measured in litres per minute, and a sort of average textbook value would be between 5 and 6 litres per minute for a resting adult human. Delta P is our pressure gradient, and we can write that now as mean arterial pressure, the pressure at the beginning, minus right atrial pressure, which is the pressure at the end. There's our pressure gradient. And then the resistance is the resistance of all of the blood vessels in between the two. And we would call that total peripheral resistance, or TPR. So here's Darcy's law of flow referred to the cardiovascular system. Cardiac output equals mean arterial pressure minus right atrial pressure divided by total peripheral resistance. Now, as we've said, mean arterial pressure is around 95 millimeters of mercury. But right atrial pressure is around 0. And furthermore, right atrial pressure doesn't fluctuate very much. So what we can do is we can actually remove right atrial pressure from the equation and we can rewrite it. And what we get is mean arterial pressure is approximately equal to cardiac output times total peripheral resistance. It's only approximately equal because, of course, I've ignored right atrial pressure here. Now, this is arguably the most important equation in cardiovascular physiology. It's extremely simple, but it's extremely important as well. And what it's telling us is that our mean arterial pressure, our arterial blood pressure, is dependent upon two things: cardiac output, how much the heart is pumping, and total peripheral resistance. Now, the important thing to remember about these last two terms is that cardiac output and total peripheral resistance are essentially independent of each other. So, for example, if you raise total peripheral resistance, it doesn't affect cardiac output. The reason for that is actually shown in the famous afterload experiments of Starling. So we talk about Starling's law of the heart, and if you look into that in more detail, you'll find that he demonstrated in his afterload experiment that you could raise the resistance that the heart has to pump against, but the heart will compensate for that, and it will maintain the same cardiac output that it had before. The important thing is that cardiac output and TPR are independent, and that means that you can use either of them to alter mean arterial pressure. Now, in fact, perhaps that's slightly the wrong way of looking at it, because under normal circumstances, mean arterial pressure is defended. The body wants to maintain mean arterial pressure at approximately the same level. In order to maintain something roughly constant, in order to control anything physiologically, you have to be able to monitor it. And in the case of blood pressure regulation, we have Barrow receptors, which are pressure receptors located at different points in the circulation. Notably in the carotid sinuses at the branch of the internal and external carotid arteries, and in the aortic arch. And these Barrow receptors will detect any change in blood pressure, and if it turns out that that's inappropriate, they will signal to the brain, and the brain will respond by changing either cardiac output or total peripheral resistance, usually both, in the appropriate way. And that can help to return blood pressure to what it needed to be. This, of course, is referred to as the Barrow Reflex, and it's most obvious if you see what happens when you're lying down and then you suddenly stand up. When you suddenly stand up, because of the influence of gravity, the pressure at the carotid sinus will drop, and that means that the baroreceptors in the carotid sinus signal to the brain. In fact, the frequency of action potentials that they produce drops, but the brain knows what that means, and it responds by trying to increase cardiac output and total peripheral resistance to try to bring pressure back up to what it should be. This, of course, is a homeostatic negative feedback response.